Hello everyone, I'm Fan Shi. You can just call me Fan. And yesterday, I think, same as most of you, we are still in summer yesterday, but today suddenly we are going to winter. But thanks for coming, for joining my talk. And today I want to share some of our recent work on simulation because we all know simulation works very well for locomotion. I was also previously a locomotion person, but recently, and why simulation still somehow struggled with manipulation. Today, what we want to show some of our efforts on this field and also some of our thoughts. So first, I want to start with these two videos. It's like recently we see like the locomotion and manipulation it really push forward a lot to show a lot of promising applications. For example, like locomotion can be super robust to do a lot of even like superhuman or some human athletic motions. And meanwhile, for manipulation nowadays, we also see a lot of new potentials to be deployed in a lot of real world scenarios. But however, meanwhile, I think maybe some of us during the Ken's talk in ICRA, actually Ken gave us some another very strict or sharp thoughts, which is still we have a huge robot data gap. First reason is like for robotics, it's like our, the dimension of data state space is much larger compared to the language model, even compared to the vision model, which means naturally we need more data. But however, meanwhile, according to Ken nowadays, you see it's like the PyZero, which represents one of the largest model, largest data set. It's like the number is like this kind of small circle compared to GPT-2, GPT-3, or even to, the one of the largest open source model. So in Ken's world, it's like, okay, for PyZero, we have almost 1 year's data, but if we want to catch up to like Kenvan, this kind of large model, we need 100,000 years data. There's a huge data gap. The question now, a challenge for every people here is like how to close the 10,000, 100,000 years data gap. So first, let's see how locomotion will solve this kind of gaps. So we saw like recently, like locomotion from 2020, 2021, it's make a great progress. Actually, most of the locomotion algorithm even today trained in the ISAC or module simulation. So for example, take this 2021 Cora paper as example. It's the first paper for LagGym. And in your paper, they claim they use 20 minutes training, and which roughly kind of 100 million samples and roughly 800 hours. And then it's like, as long as we can use 3 hours clock time with a normal GPU, we can get 1 year's robot data. And here, a question for everyone. Let's just guess, like, if you want 1 year's robot locomotion data, how much dollar you need to pay? Okay,
10,000.
$0.6. Because all the electricity only take no more than $1 for 3 hours clock time GPU running. And meanwhile, I think recently we saw a lot of manipulation cases like in China, in US, many big companies, because they are quite rich, you can hire hundreds of people to do this kind of teleoperation things. I think it's also great, but the major problem is still very expensive. For example, for this teleoperation kind of the price also including the post-processing, which is actually most costly. So usually we call it more than $100 per hour for robot data. And then again, let's guess like if you need 1 year's clean robot data, how much? The answer is $1 million to if we use this kind of use human to collect data from real world. So this is a very huge price gap, and also will trigger a lot of challenge to collect the 100,000 years data. And then here, very naturally comes the question is like, why locomotion recipe cannot directly transfer to manipulation? So here are our thoughts. We think it's the three major barriers. So first is like still, to be honest, we don't have very nice simulation actually, even today, 2026. So physics fidelity is still, how could we generate fast and accurate simulation? Still a big challenge. Second is the task scalability. For example, can task scales without the same level of the human engineering, because we are maybe based on our intuitions, like for simulation, you need a lot of human to tune to this kind of thing. So still very expensive, even you have simulation. And last thing is also super crucial. It's like for manipulation, a lot of tasks are very long horizon tasks. And compared to locomotion, it's like the reward is very hard to manually define, manually design. So could we have some reliable learning signal? So today's talk, I want to briefly share our progress on these three sides. So first, I want to talk about how to make simulation maybe more faster and accurate to be more reliable for the simulation-based learning. Okay. So first is like why the manipulation test simulation is so difficult. So if we watch about the locomotion, actually for most cases, the locomotion contact pair can be relatively easy. But however, for manipulation, many objects are deformable. When it's deformable, the context is very, very complex with a lot of contact pairs, a lot of constraints. So contact-rich tasks even today still far being solved. So I give you another example. So this example is like we just try to fold the glues with these shirts. And you can see we compare with some SXC, Newton, Genesis. Flash is our simulation, by the way. And we can see even for very simple motion, even though we carefully tune the simulation, but still the behavior is kind of very different from real world. So you can see that can very easily to generate some very weird behavior. And this weird behavior, just like machine learning, good data in, good data out, and garbage in, garbage out. If we don't have a good data, then how could we trust the learning result? That's a major issue. So in our lab, we spent almost 2 years to patiently to develop a new simulation from the very scratch level. So this is our simulation, which is a GPU native simulation where everything is writing down GPU pipeline, means it can be very fast, meanwhile can be also highly GPU parallelizable. So what is challenge for simulation? So for simulation, it's like first we need to be very fast. The real-time budget is very important. We cannot say we wait for a long time, you give me results, then it's not efficient. So and meanwhile, in order to satisfy this real-time budget, but however, we also have very large scale this deformable system to a lot of constraints, a lot of optimization need to be solved. And meanwhile, for the deformable objects and for the context, it's naturally kind of we call nonlinear or non-smooth, which just means will make your optimization problem even more complex. And then it's like we need to solve all of this big problem in very, very short time, like 60 FPS or even faster. So for our approach, I just want to briefly introduce it. It's like we use something we call local global plus non-smooth Newton. So local global is to efficiently to solve the deformable case, and non-smooth Newton in order to keep the context as accurate as possible. So in the end, after many efforts and also mathematical efforts and engineering efforts, we can make everything very fast and GPU parallelizable. And then the question is like, how accurate is this? So compared to we call the ground truth is like we run from the basic Newton method by infinite time until it converges. So it's a ground truth. So compared to this ground truth, we can achieve very low errors. So which just show us to bring some new possibility to use simulation. And another way to benchmark is like, for example, if we use for a rigid case, we can build this kind of cube on the slope, because based on the physics knowledge, we know if we want to test the sensitivity of the friction coefficient, it's like it should be 110 degrees to distinguish between slip or not slip, right? So which means if the mu is larger than a value should be get start, and then if smaller than value should get to sleep. So for our method, we can say it can be very sensitive. Oh, sorry. It can be very accurate to distinguish the sleep or not sleep to be 0.01 to distinguish it. Meanwhile, if we compare to other methods, some methods we even need to enlarge into 0.1 to 0.2 to distinguish between steep or not steep. So we try to use all of these cases in order to show how it's like the accurate for the simulation. So here is another example to compare to the medical simulator benchmark so far. It's like we can achieve very realistic, very accuracy comparison compared to the Newton method, which get converged. Okay, that's all for the basic simulation part. But as a robotic people, I think we are more interested in how to apply it. Well, could it work really in the real world or not? So since, as we mentioned, our GPU is wholly, simulation wholly GPU parallelizable, so we can also parallelize with, for example, 15090 GPU to parallelize more than 300 environments. And we can directly deploy this policy in the real world. So this is around the January this year, and we are invited to show a live demo in AAA. This year happened to be in Singapore. So we brought our robot there. We show we can continue to fold this tower from one corner to another corner. Simple for human, right? But still very difficult for robot. It's like we can continue to do it for more than 1 hour. And for this task, the whole training time is only 15 minutes, which means $0.2. You can get this nice perceptive policy. By the way, the input is a depth image looking down. So briefly speaking, the framework is like first we build our own simulation, and then it's like we build a teacher-student framework to learn from the depth image to get us how to do this manipulation task. We choose depth image because depth still the most convenient way for simple error. So for more detail, this is like some training process. In the role simulation, I want to skip to show some. So here is my favorite part. It's like the beauty of simulation is like we can simulate a lot of failure recovery case to try to cover as much as possible. So during training, because robots see a lot of failure case, when we give some disturbance, it can emerge some nice recovery behaviors. So this is the beauty of simulation because we can get a lot of this crucial data or corner case data. Okay, so first is like, okay, if we have some nice simulation, we really see some new possibility. But second is like how to scale to many tasks. Otherwise, still simulation, maybe base method still struggles. So for scaling tasks with minimal human engineering, we have three thoughts. So first is for the task creation. It's like, could we directly from the maybe real world video to generate some sim-ready digital set and environments? A second is like still there are a lot of state emission systematic application problem, how to efficiently do real to sim without even human efforts. And last is that during the inference time, could we further provide some feedback or scaling during the inference time? So first I want to show one video. This is video I borrowed from Stanley Covers. It's like this video to show, so usually it's the forward problem is like we throw a ball, we know where the ball will, based on the forward dynamics. But there's another problem is like, what if I give it the goal, could we predict like what is should be the inertial state or the parameters, physical parameters of the ball? So this one we call inverse problem. And for inverse problem, different ball simulation have a great potential to solve it because it can use a gradient from the backwards to the front. So since we have some nice deformable simulation, our nice idea could we make a deformable simulation also differentiable. So what we can benefit from it is like first is like it can be very efficient for real to sim for systematic applications. That's like the boss case, like reachable case. We can extend the systematic application also to the deformable objects. It's like giving one video. So and then we can optimize the physical parameters like bending, stiffness, and friction, and so on for this close. And then we can make the simulation ready aside to for the training and testing. And also different ball simulation can also use for the policy learning with some, this is just use some basic gradient descent to show the possibilities. And for tendon driven, it's also, we just want to show some complex cases. Like then for complex case, if you use grading, can be very beneficial. It can write a lot like SQL, blah, blah, blah. Okay. So this is for, okay, we can use less human efforts to generate the digital set. And meanwhile, for inference time, if we have the simulation, we can also, to do the scale, to do some refinement during the inference time with sampling-based MPC, or we call MPPI. So here the scaling we mentioned is like, because there is a problem we call real to sim, which is like during the inference time, how do you know the state of the objects in order to transfer to the simulation? So again, we can use large scale simulation data. We can simulate a lot of different type of the closed manipulated state, and then use this state to train a policy, train a neural network in order to predict what's the status of the state dimension of the objects. And then once we reconstruct the state of the objects, we can put into the simulation to do we can do a lot of refinement during the test time, and guided by a lot of different we call sampling-based MPC, which means you have different motion candidate. We can select the best one to refine your policy. And this post-training, this inference time method is can be very general. I mean, it can ignore any type of your base policy, and based on any policy, we can do this kind of refinement, and also super robust to the recovery case. And here, maybe people will ask again, why could I just use some existing simulation? What's the challenge? It's like, for example, we also very carefully tested like Newton, SXM, but to be honest, still the existing simulation struggle a lot to satisfy this real-time requirement, and also the stability problem. So yeah, so for this test, we use our own simulation. We just want to say still a lot of efforts is needed for the simulation part. And last example for test scaling is like we can even do co-design for with the deformable simulation. It's like once we have some nice deformable simulation, we can do the co-design together in the simulation with the hardware design and also with the policy design. So we can make a super safe humanoid robot. We can throw from the second floor, and also below is like robot can also learn some active protections. Okay, so due to time limits, some work maybe I jumped too fast, but feel free to reach out to me after the talk. So last part I want to show is like, okay, just assume if maybe we have some nice simulation, maybe we can scale very well to different tasks, just like the calibration way. But still, there is a big problem for simulation-based problem. Task is like how to generate the reliable learning signal, especially for manipulation. Most of manipulation are very long horizon tasks. But before that, I want to revisit a very famous statement or argument. It's like when I was PhD, I mean, because runtime the locomotion is also not done, right? So people say, locomotion and manipulation are inverse problem. You solve one problem, you will solve another problem. And I was very convinced at that time, but now I have some different thoughts. So first I want to compare the locomotion and manipulation. So locomotion is like for contact itself, the locomotion, as we mentioned, the contact is much simpler for most cases compared to manipulation, because manipulation, especially for the deformable objects, can be super contact rich. And meanwhile, locomotion we call self-manipulation at runtime is like it's try to self-manipulate the multi-link robot body itself. But for manipulation, it will manipulate the very high-dimensional system. And for reward design, I think this I want to talk for the third part is like for reward design for most of the locomotion tasks, not all. For most of locomotion tasks, it can be generated very short horizon, meanwhile dense reward. For example, like this working case, you just always to keep track, for example, 1 meter per second to going forward. So the reward design is relatively easy. But if we see like the right side manipulation task, it's very hard for us to manually design the reward functions. But that time I don't believe it, so I want to challenge. So go back to 2021, I want to say, oh, I think it's a maybe same problem. Could I just to solve one of the locomotion problem, we can do simple manipulation. So yeah, it really works. So again, it's around 2020, 2021, the beginning of the reinforcement learning in leg robot and the manipulation. So we can show by training in reinforcement learning, we can get very nice and robust policy against any perturbation and so on. But actually, already I have some takeaways, like it's maybe not so strict. I mean, it's not so simply we can speak as an inverse problem. First is like for contact pattern, manipulation is very hard to define. Imagine you want to throw a ball in your direction, right? It's very hard to predefine the contact patterns. But for locomotion, a lot of locomotion tests, we can define the contact pattern in advance in order to simplify the problem to speed up the training as well. And second is like what I found is quite interesting is like for locomotion, we have some very nice dense reward, but for manipulation, dense reward is even harder. So most cases, like we want goal-based, discrete goal-based reward. Okay. And then here comes again for manipulation. So how could we generate some dense reward for manipulation? So recently, I think there are some lot of efforts we can make it possible. It's like how about use neural network to provide a dense progress-based feedback. It's like during manipulation based on RGB, based on the understanding for this task, we can build very nice dense progress function. And previously, I think there are mainly three different types of progress-based method. First one is like the zero goal condition progress, which is very computational efficiency. It's just to check the difference between your current state and goal state and to see how much difference you can reduce during your motion. But the problem is like goal image can be very confused and also for long horizon reasoning is very difficult. And second one is like, how about just based on one task, we can generate a lot of task data, and then we can train a task specific. So this actually works for task-based method, but the problem is like it's very data hungry. You need specific task, a lot of data. And last one is like, okay, we trust VRM. How about VRM? VRM is great, but it has a good thing is as potential, not yet, but has potential to be generalized to a lot of tasks. But disadvantage is like the inference cost is very high and also very limited physical understandings. And here, the major problem, they all have one common limitation as well as like overestimations. So for example, like this task, when we want to grasp the bottom, but somehow failed, you can see the red one is like one of the benchmark reward model. It's very easy to overestimate. So the thought is like still today the progress function is not so robust, so reliable because of many reasons. And our thought is like, could we use the reference as an anchor in order to provide some nice confidence gating to make sure to avoid the reward hacking and make the reward more smooth. And meanwhile, we want to generate a self-supervised way in order to make sure it's more generable. So to be okay, start. Okay. So for the method itself, it's like first we use some data set and we just self-supervise use constructive learning in order to understand what kind of clips are similar, what kind of clips are not similar, and in order to use this as to compare to map for the progress. And then once we know the clips, like the similarities, it's like we can transfer to the task as well. So here is some example to show from this success case, you see our reward function can be very stable. And meanwhile, for failure case, it can very smartly know because it's confident, so it's constraints. So it's very smartly know, okay, it's failure, I should not, to provide some wrong signal from which just keep strict, to not to give you any disturbance. And for many benchmarking tasks, we show our method can learn very fast compared to existing method. And okay, I skipped one, but it's okay. So here, first, this is learning process. So because we have nice reward model, we can also deploy in the real world continue learning. So it's like after 30 rollouts, 60 rollout, and in the end, it's like 90 rollout. The policy can continue to improve itself in the real world based on this nice reward function. And even for long horizon tasks, this is also even for beginning, the robot don't know how to do it. And after 30 rollouts, still struggling. And after 60 rollout, the robot gradually learn how to do it. And after 90 rollout, the robot can already be very, nice at this kind of task. Okay. So also we have some nice closure folding tasks, but due to time, I will skip it. So in summary, for today's talk, is like we want to say is like still we see some new possibility. We can scaling manipulation in simulation. As long as we can solve these three problems very well, but first is still the simulation physics itself. Second, given a task, how could you quickly scale in the simulation? Last is like for manipulation, a lot of long horizon tasks. How could you provide a reliable learning signal in a simulation? And some takeaway is like, I think the simulation still one of the very nice way is like very high quality, but most importantly is scalable due to its very cheap data. And so far still it lead to a lot of nice real world success. And in order towards to make an intelligent and safe robot system, I think very importantly is like we need more better simulation with a lot of efforts from the whole community. And the second is like we can make the inference time refinement, and we can use differential simulation for real to sim to real. And last is like the robust and long horizon reward function can trigger the new possibilities. Otherwise, we still struggle with policy learning. And with this, I want to say thanks for all of your attention. And also I want to thank to all of my students. They did a great work. I'm just here to present on behalf of them. Thank you.
Thank you for the speaker. Any questions from the audience? Yeah, please.
Hi. So thank you very much for the great sharing. I'm actually very interested in manipulation in clothes. Is it possible to use your simulator to, for example, dress up this to a woman?
Yeah, that's a great question. So the question is like, could we also use simulation to dress up the clothes to a human? So I think it's possible. Currently, to be honest, we still are missing one thing is like human simulation, because human motion, different human or even patients, they have some very different way. But for simulation itself, it's possible because I mean the problem is like, could you simulate the soft body to contact with the rigid body, right? So our simulation has a very nice strength on this part for rigid soft combination. So short answer is yes.
But in the meantime, human may interact with the operator or with the code, and this interaction may change the dynamics.
Yeah.
So how do you look at this?
Yeah. So this one is the problem I mentioned is like still we need the dynamics, the motion pattern of the human, which is something missing in for our research, because our research we don't study the human motion. So for simulation level, it's possible because as long as you can give me the human motions, and I can, to remap to the kinematics of we can simulate human as a rigid body for this case, or even deformable body. And then it's just to solve the soft object to in contact with a rigid or another soft body. Thank you.
All right. Awesome. Here.
So for your long horizon reward functions, are you learning them jointly with the policy, or are you first learning the reward function and then the policy?
Yeah.
And if it's the second case, how much does that increase the data with one?
Yeah. So great question. So for us, it's like first we separately learn a model, neural network. This neural network is mainly to compare the clips with another, give a random clips, how much similarity with each other. So it's a separate neural network. And then during the, maybe we can call inference time. It's like inference time is like giving a task-based clips, right? And also we have a reference trajectory in just one in advance. We can use the real world data to compare to that reference data clips with our trained network. Yeah. So for the pre-trained network, I think the data set from the ImageNet. And for the detailed number, I forgot the number, but the source from ImageNet, and it's self-supervised learning, so it's like we just randomly to do some data augmentation, to do some, maybe to skip some clips in order to build this constructed learning pipeline. Thank you.
All right, let's thank the speaker again.